Hello guys, in this lesson we're going to discuss electrostatics, right? We're going to go through some of the fundamentals of electrostatics. Particularly we're going to look at some of the revision from grade 10, okay? Revision from grade 10, but we're not going to discuss much about that. Then we delve into grade 11, and then after that, in fact, electrostatics ends in grade 11. There is no electrostatics in grade 12. In grade 12, it's just revision from lower grades. Okay, so in terms of electrostatics, good people, right, what we are discussing there is charges, right? We are talking about charges in most cases, right? Now charges, right, what is a charge? A charge is something can be positively charged, okay? Something can be positively charged, which is usually represented by the symbol plus, and then something can be negatively charged, right? Which is usually represented by the symbol negative there, right? To denote that it is a negatively charged object. Now, how do things become charged, good people, right? Or what does it mean when something is charged? This means, or something can also be neutral, by the way. In the middle there, we can put neutral, which will mean that the charge is 0. Okay, something becomes positively charged when it loses electrons. Okay, when something loses electrons, it becomes positively charged. This is because electrons are negatively charged, right? So as you are removing them, that object becomes positively charged. And then something can become negatively charged through gaining of electrons. So if something can gain electrons, then it becomes what? It becomes negatively charged. Okay, so for example, let's look at a neutral element from the periodic table. Let's just take sodium as an example. Okay, sodium is denoted like this in most as a symbol, and some of these numbers here, they represent something, right? This one here is the atomic number, right? It's called the atomic number, and then the symbol is Z. What does it represent? It represents the number of protons, the number of protons and electrons in there, right? Protons and electrons in there. While this part here, right, this is called the mass number. Okay, the mass number, the symbol is A. Okay, and this one represents the number of, right, the number of neutrons. Yeah, the number of neutrons in the nucleus. Okay, in the nucleus. So now what this means is that in simple ways, this means that sodium has how many protons? Sodium is going to have 11 protons. How many electrons does it have? It's also going to have 11 electrons. So this number here, you can kind of think of it as a number that represents protons, right? And also represents electrons in the atom. Okay, let's try another one. Let's look at lithium, right? Lithium, I think, is denoted as 7 here, and then here it is 3. Okay, so what does this tell you? This means that the number of protons in lithium, they are 3. The number of electrons in lithium, they are what? They are also 3. But then if you want neutrons, you can just say 7 minus 3. You get that the neutrons are what? The neutrons are 4. Okay, so what were to happen if you were to add another electron in an element of lithium? What are you going to have? So if you do that, good people, you're going to have lithium having we usually indicate it with a we're going to say minus, right? We're going to say minus. Why are we going to say minus? Minus will tell us that lithium has gained, right? Lithium has gained 1 electron. Lithium has gained 1 electron. And because of this, we then say, oh, lithium is now negatively charged. Okay, lithium is now negatively charged.
I've got a question.
Then what were to happen if, oh yes, we are saying that lithium, right? Lithium has three, right? Remember, three protons and three electrons, right? Three protons, three electrons. If you add another electron in the nucleus, or rather in the atom of lithium, right? Lithium is going to become negatively charged, meaning that minus this minus here, we don't usually call, say, -1, but you can even avoid writing it, or you can write it like this. This part here, what does it indicate? It indicates that lithium has gained one electron. So since it's gained one electron, how many electrons does it have now? You're going to say, what are you going to say there? How many electrons does it have? It has, originally it had 3, right? You added 1. It means now it has 4 electrons. But the protons will remain as they are. Protons, they do not change. What only changes is the electrons. And because lithium has gained 1 electron, now it has 4 electrons, we say that it is negatively charged. Okay, this then the revision from what we learned in lower grades. Okay, from what we learned in lower grades. So are we okay there, ma'am? Is it clear? You need us to go through it again? All right. No, it seems like she's lost there. Right. Next, we're going to talk about what if we see Li2 plus, right? What does this mean? The plus will tell you that this means that lithium has lost 2 electrons. Okay? So when we put a plus there, it means that lost, or loss, right? Minus means gain. So if it lost 2 electrons, how many electrons does it have now? Remember, originally it had 3 electrons. It means now it has 1 electron. How many protons? Protons, they do not change. Protons are still 3. Okay, so that is what we mean. So this one now we'll say it is positively charged. Positively charged. So when you lose electrons, you become positively charged. When you gain electrons, you become negatively charged. Right? So that is what is happening there. All right, but now usually what we do, okay, what we do usually is that we take a group of electrons, right? We usually take a group of electrons, and then now we call the group of electrons, we call it 1 coulomb. So 1 coulomb of charge, think of it as a group of electrons, or rather a collection of electrons. Okay, so if something gains, instead of us saying that an electron is going to gain 1 electron, now we're going to say it's going to gain 1 coulomb of charge, right? Meaning so many electrons. Usually there are how many? 6,025 times 10 to the power, it's what? It's 25, right? Electrons. Yeah, it should be 20, that number of electrons. So it's quite a huge number of electrons. So a coulomb of charge represents a group of electrons. So when you see something like this, right, they wrote to you the -3 nanocoulombs, right? What does that tell you? What does that tell you? That tells you that the minus tells you that this particular object here, right, it has an excess of electrons. Okay, it has many electrons. How do we know that it has electrons, many electrons? Because there is a negative there. And then if something has plus, let's just say plus picocoulombs, right, maybe plus 2, let's say also nanocoulomb, right? The plus tells us that this one has a shortage of electrons, or it has lost electrons. Okay, So in simple words, when you see a plus, you can think of it as if it gained electrons. When it is minus, you can think of it as if it what? It lost electrons. Right? It lost electrons. How many electrons? 3 nanocoulombs, which means 3 multiplied by 10 to the power negative 9 coulombs, which is actually a number of will give you a certain number of electrons there. Okay, so when you see something like this, it means it lost electrons. Something like this means it gained electrons. The plus means it gained, the minus means it lost. All right, so what we usually do is that these charges, they are not really moving. They are usually stationary at a certain distance from each other. Okay, they are usually stationary at a certain distance from each other. I can call it change in x. That is a certain distance between them. As they are at a certain distance between them, you must understand that because this one has lost electrons and thus it is negatively charged, right? This one has gained electrons and thus it is positively charged. You must understand that the negative and the positive, there is some force of attraction between them. There is what? There is some force of attraction between them. Now, there is a man back in the days who came up with a law that explains the attraction between them. That man was Coulomb, and he devised, or he came up with his own law called Coulomb's law. Okay, this is a law that he used to explain what is the type, or rather what happens when charges are close to each other or they're a certain distance from each other. It's just like you and me. If I'm next to you, right, there is a force of attraction between us, and therefore it is much stronger when we are close to one another together, right? But if you move away from me, the force of attraction becomes less. This is why when people are in a long distance relationship and this one is back in KZN while this one is at GP there, right? Because they are very far away from each other, it's very, very much likely that the relationship is not going to work out, right? You find that this one here, right? This one here is here, right? And then this one here is here. This relationship is not going to work out at all, because imagine I have to take a taxi that will take me how many hours to reach to you there. Understand me? So that is what we call by the force of attraction. Okay, the force of attraction there. I hope it is clear. We can even remove these, good people. We can even remove this and then take some, like, say hey, no, UJ will take down my video. Let's just continue, good people, right? So let's continue with this, what we call a Coulomb's law. Okay, so we said it's just a law to explain the force of attraction. Now, what does Coulomb's law state, right? Coulomb's law state that now we need to state it in terms of those definitions, right, that are prescribed in your curriculum. Good people, you must understand that in physical science there are predetermined definitions that you must give, right? So you must ensure that you list them as they are, right? So I'm going to give you one here, right? If I can just put it out to you there, right, in just in a second. Let me maybe write it here, right? Let's put it here, right? So this is what Coulomb's laws say. Okay. Okay, let's take this a bit back there. Oh, okay. the magnitude of the electrostatic force exerted by one point charge on another is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Yes, yes. Yes. So please try to ensure that you memorize this definition, good people, right? And then after that, we shall then understand that it can also be described in terms of symbols, right? So in terms of symbols, you can write it in this way. So you can say F is equal to K Q1 Q2 all over R squared. This is Coulomb's law. It says this force, right, the magnitude of the electrostatic force, which is this force, exerted by one point charge Q1 on another. So this means that you have 2 point charges, right? It could be a point charge or it could be a charge itself. To say this is Q1, right, and then this is Q2 there, right? Q1 and Q2. We are saying the force between them, or the force of attraction between them, the magnitude of the force of attraction, the magnitude of the electrostatic force exerted by one point charge on another, is going to be directly proportional to the product of the magnitude of the charges, right? To the what? To the product of the magnitude of the charges. Product of the magnitude of the charges. This is the product of the magnitude of the charges, right? So the force is going to be directly proportional to that, and then inversely proportional to the square of the distance r between them, and inversely proportional to the distance. So what we mean there, right, is that the larger the sizes of the charges, the more the force of attraction. Put it in this way, right? If you are going to be in a like a relation, right, with someone who has a lot of fat, right, you guys are definitely bound to last for an eternal lifetime. Okay, the problem becomes when the man is very skinny and then the lady there is a bit, muscular, so it not has a bit of some fat, right? So in that way it becomes a bit tricky, right? So in terms of the charges, that's what we're saying. We must have the product being a very high, and it can be very high if both charges are large. So the larger the sizes of the charges, the more the force of attraction, right? Just as a disclaimer, good people, right, I am not throwing shade at anyone. This is just to illustrate the or rather to assist you to view this practically, because I like things that are practical, you understand me? But it's not a disclaimer, it's not even a bad thing to have a nice there. All right, so the distance also matters, right? If it happens that you guys are close to one another, for example, you stay together, the force of attraction is very much high. It's the same as if the charges are close together, the force of attraction is very much high. But if they are far from one another, then it means that the force is going to be less. That's what we mean by saying inversely proportional to the square of the distance between them. I hope this is clear, good people, right? So understanding that will then assist you to say, oh, okay, so if I'm giving a charge here, let's just say I'm giving plus, they always show you this plus or minus to say that whether that thing is positively charged or negatively charged. So let's say we have this one here, and then let's just say we have this one here, which is negative 2 microcoulomb, right? Now, what would be the force between them? What would be the force between them? We can use Coulomb's law to find out. What is the electrostatic force between them? The force is called the electrostatic force. Electrostatic force. The force is called electrostatic force. So we can use the force, we can use this Coulomb's law to get what is the force between them there. All right. Oh, sorry, now I'm thinking about universal law of gravitation, sorry for that. Q1, Q2. This is because this formula is very much the same as universal law of gravitation. So good people, K is a constant. It's called it's always 9,0 times 10 to the power 9, right? So you just substitute it there. It's given at the in your question paper, right? Q1 is going to be 3 multiplied by 10 to the power negative 9. Remember, nano means you multiply by 10 to the power negative 9. Micro means you multiply by 10 to the power negative 6. Milli means you multiply by 10 to the power negative 3. Pico means you multiply by 10 to the power negative 12. Okay, so in this case there, right, this is what we have. And then for Q2 it's going to be should I write it like this? And then the distance, let's just say the distance between them is meters. We always use meters, good people, right? So we're going to say 10 meters squared there. Good people, can someone tell me, do you see anything wrong with this formula or how we substituted? Yes, ma'am.
You don't have to put the negative sign on it.
Right, very much correct there, Miss Ladi. Thank you so much, right? We do not do these, good people. We do not include the negative sign. Okay? We only put positive values there. Don't include negative signs. Okay? Please remember that. To say you never put negative on this formula there. It's just positives only. The negative can be on the exponents like that, but not either here or there, right? You don't put negatives there. Perfect. Then you can quickly run to your calculator and punch in those things there and make sure that you get the final answer from that, right? Of which now it will give you the correct answer there. So you can do that, right? What is 9 times 3 is 27 times 2 is going to be 44. 54 divided by 100 is what? 54 divided by 100 is going to be 0,54 multiplied by 10 to the power negative 6, right? Which means this is what? This is 5,4 multiplied by 10 to the power negative 7 coulombs. Do you get something like this, good people? It should be negative 5, not negative 7. Negative 5. Do you get something like this? Nice stuff, good people, nice. This part, when I calculate, I don't like using a calculator because I know I'm a calculator myself. Now let's go further, good people, and try to do some more examples, right? We're getting the gist of what is happening here. Let's just say here that we have it as minus 3 micro. Why do I like 3? Okay, minus 4 microcoulombs, right?
And please go back.
Yes?
Please go back.
Here.
I just want the final answer.
Oh, okay, all right. Is this one here 5,4 times 10 to the power negative 5 coulombs?
Okay.
Right. So let's just say here we have a stand, right? They can tell you you have an isolated stand with your what? With your charge there, and then let's say you have this one here, right? Another one, and then this one is plus 2 not micro, let's just say nano coulomb, right? So let's just say the distance between them, right? They give you that the distance between them there, is around 5 meters, right? Oh, still gonna use 10 oh no, let's say 100 centimeters, right? So let's say you're given something like this. You must calculate the force of attraction between these two charges, right? How are you going to do that, right? Coulomb's law assists us because he tells us that when these things, they are placed next to each other, the force of attraction between them is going to be inversely proportional, is going to be directly proportional to the product of the magnitude of the charges and inversely proportional to the distance between them. So this is what we have here, good people, right? And then now, did I say 100 here? Divide by 100. Oh, that's okay. How do we move from centimeters to meters, good people, right? Let's remember that King Henry once died a miserable death called malaria. And from here, good people, right, this is centimeter here. Centimeter is here, and then this is what we have. So this means that 1 meter is actually equal to 100 centimeter there. So it means that to move from, in simple words, to move from centimeters all the way to meters, you just have to divide by 100. Right? Very important skill we must apply there. Now, K is equal to, remember K is 9,0 times 10 to the power 9. And then Q1 is what? Don't put negative. You put what? You put 4 times 10 to the power negative 6, because that is micro there. And then that side you have 2 times 10 to the power negative 9, right? Then you're going to divide by 1 squared. Where do I get the 1? Because this is 100 centimeter, I divide by 100 to get meters, right? Then from there, what you must get as the force. Oh, good people, let's not make this mistake. Force is measured in what? Force is measured in newtons. So we use newtons there. So sorry for that. Force is newtons. Okay. So we go here, right, and then we say 9 times 4, 36, right? 36 times 2 is going to be 72. Now 72 divided by 1 is just 72. So you have yourself 72 multiplied by 10 to the power negative 6 coulombs there, right? Of which it's usually written as 7,2 multiplied by 10 to the power negative 7 coulomb. You see now, why do I like coulombs? It's newtons. Sorry, it's what? It's newtons there. Is that what you get? Please confirm that for me. Perfect. Perfect. So now that is what we do when we are usually calculating for this. So you must just know how to use this formula there. But wait a minute, right? Wait a minute. What if we actually say, okay, right, we have these 3 micro coulomb, right? And then we have this one here, negative 6 nano coulomb, right? And then we say we have a third one, third one, right, which is a 5 micro coulomb, and this is negatively charged, and then this is positively charged. Now there are 3, right? So what do we do when there are 3 now? When there are 3, good people, right, remember they are not only exerting forces between them, right? We are now going to have actually what you call a net electrostatic force. because there are so many forces that are now involved here. A net electrostatic what? Force, which is usually called just F net. Ne? So F net is usually equal to F1 plus F2 plus F3, etc., etc., depending on how many forces that you are dealing with, right? So let's look at these three here, right? Since there are three of them, right, we need the distances, right? Let's just say the distance here is 6 meters, and then let's say the distance here, let's just say it's 5 meters. Okay, it's 5 meters. Now questions are going to come in such a way that they are very much specific to say what do we actually want or what are we looking for. Okay, so they will tell you that to say, given the scenario above, right, calculate the net electrostatic force experienced by the -6 nanocoulombs charge due to the two charges on both sides of the charge, right? So these are questions, this is how questions usually then come up there in your test exams, etc. there. How? All right. Calculate the net electrostatic force experienced by that. Let me write this actually on top. Right. So now that they want from us the net electrostatic force experienced, you must just ask yourself, it's experienced by what? My question is always, it's experienced by what? Who is or which charge is experiencing the force, the net electrostatic force? Which charge is experiencing the force? I'm actually going to call this number 1. Good people, the net electrostatic force, it's experienced by which charge? It's experienced by the -6 nanocoulomb charge. It's experienced by this one. Since it's experienced by that one, you're going to draw your free body diagram on that one because it's the one experiencing the force, the net electrostatic force. I hope that is clear. So you're going to say, okay, I'm going to draw my free body diagram there. Right, so you would say here that you have this represents that charge that is experiencing the force. Then you ask yourself some simple, nice questions, right? You're going to look at the 3 microcoulombs, right? And then you ask yourself, what is the 3 microcoulombs doing to this one that is experiencing? They said by, again, by this one. So this one. So what is this one doing to this? What is happening? What is it doing? Since it's positively charged, ne? If it finds that this one is negatively charged, since this one is negatively charged, this one is going to say woza kimi, which translate, that is like Afrikaans way of saying come to me. You understand me? So this one is going to say woza kimi. This is because it's positive and this one in the middle it's negative, right? So unlike charges attract, so it's going to say come do it, right? So we're going to show that with an arrow to say they said to me come do it. So we just maybe use a nice arrow here. Actually, my arrows are a bit problematic, but that's what we have. Who is saying come do it? This is 3 saying come do it on 6. That is how we represent that. Okay? This is saying come to me. And give you a negative when come to me. So this means that is the force of 3 on 6. Come to me. Then we go this side to the west, right? To the east, right? On the east side, right? On the east side, what is this one doing? What is its charge? Its charge is negative. I get. What about this one? This one is negative also. So since this one is negative, ne, the way I always thought of this is to say, if they say calculate the net electrostatic force experienced by this charge, that charge that they are talking about there, it's more of like it's going to be shell. Okay, right. It's going to be coating. Yeah, it should be that way. It's going to coat the others. Ne? It's going to coat the others to say. So again, it's gonna go here and say I'm negatively charged, right? What do you say? Then this one is gonna say no, can't do the right, because you are having a negative, an opposite charge to me, right? Then it goes here and says I'm negatively charged, right? This is the one talking. I'm negatively charged, talking to this one, right? Do you agree or not? This one says but I'm also negatively charged. I know. Hamba, right? So that one will say go away, right? And then we'll show that by an arrow here to say it's saying go away, angikufuni ngoba wena you have the same charge as me. So this will be the force of 5 rejecting what? Rejecting 6. So everything, what is very much important is to understand that this is the one that is going to be experiencing those rejections or those attractions, because they said by that charge. I hope that is clear, good people. So now that you have 2 forces, right, the rest is history. You are now going to say, okay, I have to calculate the net force, right? But you have to choose your direction. So we're just going to choose to the left as positive. Okay, to the left as what? As positive. And then we're going to use the formula there. We would then say, okay, let's start by f of 3 on 6. F of 3 on 6, right? This would be k q1 q2 all over r squared, right? 9,0 times 10 to the power 9. Q3, right, is going to be 3 times 10 to the power negative 6. And then 6 is going to be 6 times 10 to the power negative 9, because it's nano, right? And then here the distance is 6 meters. All right, then what do you do there? You multiply. So you're going to say 9 times 3 is 27. 27 divided by 6. Yeah, that one is going to be problematic. 27 divided by 6. So it's going to be 4 comma something, 4,3. 4,5. Is it 4,5 times 10 to the power negative 6 coulombs? Can you check for me, good people? It's 4,5. Oh, nice. Right. So that is what we have, right? But you're not done now. You have to go to the force of 5 on 6, right? So for the force of 5 on 6, right, you then say k q1 q2 all over r squared, right, of which now you're going to say 9,0 times 10 to the power 9, right? Q1 5, right? Q5, right, is going to be 5 times 10 to the power negative 6, and then the other one is going to be 6 times 10 to the power negative 6, right? And then you're going to divide that by 5 squared. Okay, a lot going on there. 9 times 5, 45. Oh, wait. 9 times 6, 45, 54. So 54 divided by 5, good people. It's going to be 54 divided by 5. Is it 54 divided by 5? 10,8. 10,8. Multiply by 10 to the power of 9 minus 6 is what? It's 3. 3 minus 6 is negative 3. Is it something like this? Oh, why am I writing Coulomb? Yo, good people, now I don't know what happened. I don't know why I love Coulomb. Good people, the force is newtons. I get it's newtons. I'm very, very sorry for this. I don't know what is going on with me for real. All right. What is this correct? Or what is the correct answer? Oh, nice. People, I attended, I was in Maths Olympiads for a longest time now, Right, so F net, right, we then say it's going to be equal to 4,5 multiplied by 10 to the power negative 6 plus 10,8 multiplied by 10 to the power negative 3, right? Then you just put it in your answer, because F net is just to add all of them, and they're all positive because I said left is positive and all of them are going to the left. So from there, right, I think you can say, you can be calculating it that side so that you tell me the answer, because what I'm doing here might not work out for me, right? But I'm just revisiting some of my skills there, right? 4,5 negative 3 1 2 3 0, 0,0045, right? Plus 10,8, right? So that should be 10,8045, right? Yeah, so in essence it should be 10,8 multiplied by 10 to the power negative 3 newtons there. I don't know, good people, it might be very much wrong. What is that? Oh, it's correct. Yo, nice. nice. Ngiyaphakamisa, good people, right? Nice stuff there. All right, so that is the net force, good people, right? But you can even include direction to say to the left, okay? You can even say to the left there, right? Oh, and by the way, this is what you must do if you are writing in BT, try to work mentally without a calculator. All right, good people, that is how we work these problems out. I hope you can see that they are not really problematic. What you just need to make sure that you know is that where are the directions. We can even change this scenario. Oh yes, you can ask. Yes, Miss Clary.
What if we are treating the force experienced by the negative 5 mu c charge
So
instead of negative 6?
you are saying?
Sir, what if we at the question we write by the negative 5 mu c charge instead of negative 6?
Good. That's the question I was coming to. That is the question I was coming to. You read my mind, man. Right. So we're going to take the very same thing, good people, and then we're gonna twist the question just a little bit. Right. We're gonna twist it just a little bit. Now, this question, right? let me remove this question. Instead of it saying by the -6, right, what if it said by the -5 and then microcoulombs there, right, which will be, I'll fix it in a second. Microcoulombs, micro is something that will be like this. Get? So what if it says that what is calculate the net electrostatic force experienced by the -5 microcoulombs due to the other charges or on the other sides, right? Let me write due to the other charges, 3 microcoulombs, positive 3 microcoulombs, and -6 nanocoulombs. All right. So in this case, now we're saying what will be the net electrostatic force experienced here. So this is what you do. Since they said by this one, that is where you're going to draw your free body diagram. Okay, then you're going to say, okay, let's start with this one. This one is going to come to this, no, sorry. So the one that is experiencing the force is going to come here and say, I am negatively charged. Do you agree or do you not agree to be with me? This one says, but I'm also negatively charged. No, go back, and it's funny. So it means this will be pushing that side. So this will be the force of 6 on 5. Then he says, okay, it's fine, you rejected me, it's fine. I will go to this other one. He goes here and then says, Ash, I'm negatively charged here. And when I see you're positively charged, do you agree or you agree not? This one says, I'm positively charged. We are meant to be together, soulmates. Come do the wozala. And then he does this, right? So this will be the force of 3 on what? On 5. Okay? Then now we have a nice scenario that is looking like this. The rest is calculations. Okay? So we are going to choose direction. I'm going to choose maybe to the right is positive, right? I always like to the right to be positive. And then we're going to calculate our forces, right? Now we're going to say, number 1, the force of 3 on 5. We use the same formula, Q1, Q2, all over R squared. Remember, K is 9,0 times 10 to the power 9. Q1, right? Q1, which is 3, right? You can even write 3, 5, but usually no, write it the formula as it is, right? So we are going to start with 3. 3 is going to be 3 times 10 to the power -6. And then Q2, right? 5 is going to be 5 times 10 to the power -6. Okay, what is the distance between this and that? This total distance here, good people, is going to be 6 plus 5. So that will be 11. Okay, that will be what? That will be 11 squared. 11, now it's going to be, but 11, is it that difficult? Okay. So you're going to then multiply there, right? 11. It's going to be difficult for me, right? But then can someone maybe assist me there? 9 minus 6, 3, and then you have minus 3 there. So essentially you have 9 times 3 times 5. 9 times 3 times 5. So what does that give you there? Big numbers, very odd numbers. Yes, ma'am. Mm-hmm.
It gives me 0.00115. Three ones, sorry.
uh,
7 0 2 4 7.
all right, so you're going to need to put this in scientific notation. Okay, we usually recommend using scientific notation because that's the first thing we learned in physics. So now it's going to be 1 2 3, right? So this is going to be 1 comma 1 2, right, multiplied by 10 to the power negative 3 newtons. Okay, that is what we're going to have there. 1 comma 1 2, yeah, that is the one. And then right, then we go to the force of 6 on 5, of which now that one will be k q1 q2 all over r squared, right? And then we're going to say 9 comma 0 times 10 to the power 9. We're going to divide that by q1, or rather by the first one, which is 6, right? 6 will be kind of, what is 6 there? 6 times 10 to the power negative 9 multiplied by q2, or the second one, which is 5, right? Because it's 5 again. 5 times 10 to the power negative 6. It's micro again. Yeah. Then you divide by, what is the distance between them? You can see the distance between them is 5. So we're going to have ourselves 5 squared. Jojo. And then that one, that is a nice one, right? To say 54 divided by 5, right? 54 divided by 5. So if you say 54 divided by 5, that will give you 10.8, like we had before. And get, so you're gonna say you have 10.8 multiplied by 10 to the power negative 6 newtons. I hope that is correct. Should be 45. Yeah, that should be the one. So this is the force, and then that is the force. Then we can calculate the net force. Therefore the net force is going to be 1,12 times 10 to the power negative 3 plus 10,8, right, multiplied by 10 to the power negative 6, which is going to be 1,12 plus 0,0108, because that is 3 there. I get 1 2 3, yeah. And then from there the final answer will then be 1,13 multiplied by 10 to the power negative 3 newtons, right? Please check that for me. 1,13 times 10 to the power negative 3 is negative 3. Is it correct? Great. So that will be the net force, and since it's positive, the net force is to the right. Okay, great stuff, good people, great stuff.
Sharp.
Sharp.